Hello dear students, welcome to Pen and Paper Chemistry. What is the topic that we are going to take up today? Properties of haloarenes is what we are going to discuss in this session. So please get your pen and paper ready, pen and your notebooks ready to take down notes for offline reference. When we talk about the properties of haloarenes, what we have to see is what are the possible reactions that a haloarene can undergo. So, first possibility is if a nucleophile, a nucleus loving species, that means something which is carrying a negative charge or has lone pair of electrons, comes and replaces the halogen. So, one possibility is replacement of one nucleophile by the other. The second possibility could be an electrophile, that means an electron loving species, something with a positive charge or vacant orbital, coming and taking the place of one of the hydrogen atoms in the ring. So, we have E over here, right? So, when the replacement is happening by a nucleophile, so it would be called as nucleophilic substitution reaction. A substitution reaction taking place through a nucleophile. On the other hand, an electrophile replacing the hydrogen would be classified as electrophilic substitution reaction. Now, what kind of reactions do haloarenes prefer to undergo? If you notice over here, the benzene ring is electron rich. Why is it electron rich? It has 3 pi bonds. What are these pi bonds? The double bonds that you see inside the ring. 3 pi bonds means it is itself electron rich. It has a ring of electron clouds above and below the ring. Now, because of this electron cloud above and below the ring, do you think that it will allow the nucleophile to come and attack the halogen which is attached to it? It will not. It will not entertain the nucleophile easily, right? So, we will have to bribe these electrons, divert their attention and then make it possible for the nucleophile to replace the halogen. In other words, although haloalkanes undergo nucleophilic substitution very happily and very readily, haloarenes on the other hand do not tend to do so. They are repelled by the idea of being substituted by a nucleophile. What about electrophilic substitution? Now, electrophile means something which is wanting electrons, and this has a rich supply of electrons because of the pi bond. So, what will happen? It will easily and happily call electrophile and say, come on, let's form a bond, let's make a new friendship, right? So, what kind of reactions would you expect to see more in the case of haloarenes? Yes, electrophilic substitution reactions. Now, if any of these terms, that is nucleophile, electrophile, electrophilic substitution, sound alien to you, don't worry. I've already put videos on the channel to explain each of these concepts very clearly in easy to understand format. So, please don't forget to visit the playlist Basic Concepts of Organic Chemistry. Haloarenes are less reactive than haloalkanes towards. Now, we can complete the sentence. Yes, towards nucleophilic substitution reactions, right? So, what are the possible causes for it? As we said, there are double bonds. Double bonds means the carbon to which the halogen is attached is an sp2 hybridized carbon. On the other hand, in the case of haloalkanes, the halogen is attached to a carbon which in turn is just sp3 hybridized. So, sp2 hybridization means the carbon halogen bond length would be shorter, they would be more closely attached. On the other hand, in the case of haloalkanes, the carbon halogen bond length would be longer. So, in other words, what we've got is we've got these two cousins who are a little further away from each other compared to the cousins over here who are very closely attached. There's a strong friendship between them. Or what we say is that there's a stronger friendship between them compared to in the case of haloalkanes. So, it will be more difficult to break the bond in the case of haloarenes rather than haloalkanes. Another factor which comes into play is resonance. Yes, if you are new to the concept of resonance, it's just like the monkey in the middle game, right? So what we have is we've got these players here and we've got a ball being tossed around. Now what I do is I try to enter into this game and I want to take charge of this ball. Person A has the ball. As soon as the person sees me trying to grab the ball, he throws it to B, right? Now I move towards B, but when I go towards B, B is very smart, throws it towards C. In other words, what is happening is the ball is not remaining confined to any one player, so I end up going here, there and everywhere, and the ball has greater chance of remaining in between these three players rather than coming to me. Apply the same concept and same fundamental to a benzene ring which has alternate double and single bonds. I've got a group attached over here. What will happen? The lone pair of electrons on the halogen move towards the benzene ring. With the result, now what will happen to the double bond? Yes, it will move towards the carbon. So let's put a negative sign over here. This has turned into a double bond, 1, 2, 3, 4 and a positive. The other two bonds remain unchanged. Let me leave it like this. Let me not touch them. Now come to the next one. He says, oh my God, I have a negative charge. I can't be alone. I need to form a bond. So he says, okay, either it can form a bond again like this one. The other possibility is the pi electron now is used to form the bond here. Correct? Now, so that means the electron on the other hand will move to the carbon at the bottom. So let's draw the next structure. So we've got the negative over here, very much in place, the halogen, and now what is there is there's a double bond here, there's a double bond over here and a negative charge as well. Correct? Now there's a fourth possibility as well. So we have here this electron now will want to form a double bond. It says I don't want to live alone, I want some partner. So if it forms a bond with, okay, let me number these as 1, 2, 3, 4, 5 and 6, right? Now if carbon number 4 tries to form a friendship with 3, I'll have this same structure. At the same time, there's a possibility that it will form a bond with carbon number 5. So here we go. So with the result, we will have a double bond here untouched, a double bond X with a positive charge, and we will have the electrons over here. because the double bond is now, the electrons of this carbon are being used to form a double bond with carbon number 4. Now it's carbon number 4 and 5 which are forming a double bond. Still confused about resonance? Don't worry, there's a separate video on resonance to give you some practice about it and to also widen your knowledge about it. So please do visit and do watch that video in case you have any doubts. At this point of time, I will stress on the fact that resonance is a very, very important concept in organic compounds and you cannot avoid it. So better it is to clear your fundamentals on that concept. So now because resonance is there, it's just like the ping pong or the monkey in the middle game. Now if any of the nucleophile will want to come and attack the benzene ring, where will it go? Which carbon can it attack? Not easy to do that, right? That is why we have written that the haloarenes are less reactive towards nucleophilic substitution than haloalkanes. I hope you are noting this down for future reference. There you go, your favorite flow chart. But this is not complete as yet. No, this is not the complete chart. What I want you to do now is to try and write these reactions. So what we've got over here, we've got the haloarenes and we are talking about their properties. So haloarenes being converted to different compounds by electrophilic substitution reactions, nucleophilic substitution, reduction, and there are a few miscellaneous reactions here and there. Electrophilic substitution, replacement by an electrophile. Wherever you see these, remember these 5. That's it. What is it? Halogenation, nitration, sulfonation, FC alkylation and FC acylation. Friedel-Crafts alkylation and Friedel-Crafts acylation. Remember them. We have already spoken about them in detail under the topic of benzene, and we have also covered the mechanisms of each of these reactions under the set of videos on basic concepts of organic chemistry. Any doubt? Pause the video now, watch the properties of benzene, clear your fundamentals, and now try writing the reactions for each of the 5 electrophilic substitution reactions of haloarenes. Halogens are ortho-para directing groups. So, I have the halogen already present on the benzene ring. The position next to it is ortho. So, it can be this one and it can be this one. 2 positions next to it would be meta, right? 1, 2, 1, 2, right? Okay. And the third position, that means the third position next to it would be para. So, we've got the ortho, the meta and the para. Ortho, meta and the para. So, there are 2 ortho positions, 2 meta positions and 1 para position with respect to the halogen already present in the benzene ring. Halogen atoms are ortho-para directing groups. Why? Why is the question. I am not giving you the answer because I want you to explore it yourself. To help you again, there is a separate video, watch it, ortho, meta and para directing groups and clear your fundamentals. There is no point in memorizing all this and just gobbling it up. No, You need to understand, you need to make learning easy for yourself, not difficult. So I will encourage you to write, to understand that topic. So we've got the halogen. The electrophile can attach itself to the ortho position. That means it replaces the hydrogen at the ortho position, or it replaces the hydrogen at the para position. So we can have two products possible over here. So we've got the ortho product and the para product. Of course, in most of the reactions you will find that the para product will be the major one. Why? Look at the distance between them. They are far apart. So there will be less repulsion between the atoms. They won't start fighting with each other. Here they are close together. So close together means there will be a lot of repulsion, there will be a lot of infighting between them. So they would prefer and they would be happy when they are further apart from each other. So now, before I come back with the next video and clear your doubts, write the reactions of halogenation, nitration, sulfonation, Friedel-Crafts alkylation and Friedel-Crafts acylation. Keep your equations ready and I will give you the answers and we will tally the reactions. So what will be important in these reactions would be the reaction conditions and the products of this particular reaction. This is what I am looking towards when we discuss the products of each of these 5 electrophilic substitution reactions in the next video. So stay tuned, stay connected till then and make sure that you watch the ortho meta para directing groups video on the channel and stay ready for the next topic. No, a continuity of this topic. See you soon.